Greetings everyone, this is Non-Expert here, back again with another video. Today we are going to be solving problem number 58 and difficulty it's been rated at is medium. This problem was asked by Amazon and let's just dive right into it. So a sorted array of integers was rotated an unknown number of times. So given such an array, you need to find the index of the element in the array in faster than linear time. If the element doesn't exist in the array, you need to return null. So we've been over here and the array is a rotated sorted array, and if you don't understand what a rotated sorted array is, it's pretty simple. If you sort of look at this, you can sort of visualize this as well. So if you see the part which I've highlighted over here, this particular sub array is supposed to be sorted, and if I sort of look at this particular guy, this thing is also sorted. But if I push these elements 13, 18, and 25 to the end of the list, you will get 2, 8, 10, 13, 18, and 25, which is basically a sorted array. So basically, you could sort of think of this as there's a particular pivot element, and your starting index has been pushed at that particular pivot element, and basically all those values have been pushed accordingly. And that's basically it. A rotated sorted array is very easy to understand because you can sort of visually look at it and you can see it over here. And it's been given an example over here that if you have an array like this and an element or target value as 8, you need to return 4, basically where that value 8 is going to reside, or which index it's going to reside at. So obviously you can sort of iterate through each element and do this in O of n complexity, um, and just find the element, but that's not what they're asking you. They want you to do it faster than that. And whenever you get a problem like this with a few constraints, you just have to look at the tools which are there in your arsenal. So most of you would already understand what a binary search is, and binary search sort of works at a complexity of log of n. It's faster than O of n, obviously. But you would be asking this question that how would you understand that, how would you implement the binary search solution? So again, before we sort of dive into that, fortunately we were able to find a similar question on LeetCode, and the name of the problem is search in rotated sorted array. And again, as usual, I would urge you to pause this video and check out the link given in the description below and try solving this problem on your own. But over here also you can sort of look at this and they sort of explain the same thing. You may assume that the duplicates which are there inside this array, and that's a little bit important. But the algorithm's runtime complexity must be in the order of log of n. So basically, they are urging you to do this in a binary search sort of a way, a customized binary search sort of a way. And you've been given a simple example over here. And as you can see over here, that the part which I've sub highlighted, if you sort of push it at the back of the list, you would get a sorted array. Now, before we sort of get into the solution, let's just type in a few things so that we understand or we have a few rules in place. So what we're going to do is we're going to implement a customized binary search solution, and the binary search solution sort of works on the premise that there is always a mid, which is being construed by your low and high elements, and you just take their, you just add them up and divide them by 2. That's the middle that you have, and then you sort of understand whether your value, whichever target value you're sort of looking for, whether it sort of lies on the left hand side from low to mid, or whether it lies on the right hand side, which is from the mid to the right. So pretty simple, but over here you need to make sure about a few things. uh, and the reason why I'm sort of urging you to pause this video and try doing this on your own is because of this particular edge case as well. So before I tell you the edge case, if you look at this particular example, if you look at the midpoint is here, right? So whatever you have on the right hand side, that's sorted, and whatever is on your left hand side, that is also sorted. Might not be sorted in the way that you would like, but they are sorted as different sub-arrays. So if you divide and conquer this approach, you're sort of getting that value. But you might not always have the solution where the middle point is your pivot element at which you can everything around. So take this particular example for our use case. So let's just say if we have 7, 1, 2, 3, 4. So this is also rotated sorted array because the one which I've highlighted over here is sorted, and this guy is also sorted. And if I sort of push the 7 at the back, which I can, it will sort of become a sorted array. So in a way, this is a rotated sorted array. But if I take the middle element, which is 2 over here, you can see for a fact that the right hand side is sorted, but the left subarray is not sorted at all. So that's something that we want to take care of. And our entire implementation is sort of going to work on this premise that we're first going to look for whether the left hand side or whether the values or I don't know, whatever you want to call it. You just want to say that, hey, where the values from low to mid, if they are all of them are sorted, then you could sort of make sure that you look for that particular target in your way. And that's very easy to do because all you want to do is, if this guy is already sorted, you know for a fact that you might get a case that nums mid to basically the right side. Let me just write this down. So you may already understand that this might be unsorted, this particular right subarray, if it's a rotated subarray, right? But if this guy is not sorted, if the left hand side is not sorted, then definitely the right hand side is always going to be sorted, because the way the rotated sorted array is working, it's only rotated, or its pivot point only lies in one place. So if you find that pivot value, if it's on the left hand side, then the right hand side is going to be clear, it's already going to be sorted. But if it's on the right hand side, then the left hand side is going to be clear, it's going to be sorted. I hope that sort of makes sense. But the way we're going to go about it is that if num's length from low to mid is already sorted, then you want to make sure for a fact that the target value that you're looking for is within the range from num's length to num's mid. And that's very easy to do. You can just check for the target value from low, whether it's greater than or equal to all those values, and then understand whether it's in that range. If it's not in that range, then obviously you sort of go to the value which is next, which is from mid plus 1 to high, and that's your entire approach. So that's the divide and conquer approach that we're going to be using, and this is get down to the implementation, right? So as usual, we're just going to write our base condition for this particular function, which is just going to be, hey, if nums has not been given to us, then we return -1. Now what we need over here is a utility function. So let's just make that. Let's just say, hey, we have a search util which just takes the low and the high. Now I'm just writing low and high as L and H. It's pretty easy to understand. Um, Actually, let me just write it as low and high only, so that's easier for everybody else. So you have low and high. You don't really need to pass in the nums and the target value because they're already accessible to you as they're part of this function. So they'll be accessible to the search util function as well. And what we're going to be doing is, whatever this search util function is going to return, we're basically going to return that as our result. So over here, as we do in binary search, the low value is always the first index, which is the 0, and the high value is the last index inside your nums array. So the way to do that is just write length nums -1. And yeah, that's pretty simple to do. Now over here, we need to make sure that we're handling the search utils base condition. And the base condition is a simple base condition which everybody has inside whenever you're coding in a binary search sort of a way, which is, if the low is already greater than high, then you want to make sure that you return -1. Basically, you've been iterated through everything else and you were not able to find that particular target element. The other thing is that you want to formulate a mid element, which is going to be low plus high divided by 2. So this particular division is sort of going to return an integer representation, and that's really important for us. If you don't do that, you'll get a float representation, and if you use that value inside your array, it's going to just throw an error. So this is going to be an int now, and you want to make sure that whether the nums mid is already equal to the target value. So if it's already equal to the target value, and know for a fact that I just need to return the mid, which is the index at which we found the target value. And if it's not, then we're just going to work on the rules that we've already dictated, which is that we're going to check whether the length, or sorry, the sub array which is on the left hand side from the mid, whether that is sorted or not. So let's just do that. Let's just check that. Let's just say, hey, if nums low is less than equal to nums mid, and we don't really need the less than equal to, because we know for a fact that all the elements are unique over here. But if you've not been given that particular case, then you want to make sure that it's less than equal to. So if nums low is less than equal to nums mid, then you can make sure for a fact that this is obviously sorted. Pretty simple to understand. And now what you want to do is you want to check whether the target value which has been given to us, this guy over here, whether it's sort of is within the range between these guys. So range calculation is very, very easy. All you have to do is you just have to say, hey, nums low, and we're going to do this in a Python way where you can just say less than equal to target, which is less than equal to nums mid. And if this returns, this is just one way of doing it. You can sort of divide this into two if conditional operators. That's on you. But I like this way because it sort of signifies that you're checking for that particular change. So all you're doing is you're just checking, hey, if num's low, sorry, so if nums low is within the is less than the target and nums mid is greater than the target, that you know for a fact that your target is going to be in the middle if it's going to be there at all. And all you have to do is you just need to return your recursive implementation to look for that element now. So all you need to do over here is you just need to update your high value, which is going to be now mid minus one, because it's going to occur between those guys. And if it's not over there, then you want to make sure that you're calling the correct place. So now the low is going to get updated to mid plus one, because obviously it does not exist over here from this guy to this range. So if it doesn't exist, then obviously it's going to be in this range next. So you just call that function accordingly, and that's just the way to go about it. Now, if this is not the case, if you don't come over here, you can make sure for a fact that values which are on the right hand side, the right subarray, which is from mid to high, all those values are going to be sorted. And if they are sorted, all you want to make sure is that whether it sort of comes within that range as well. So just check for the target value whether it's in the range. So you just say, hey, nums mid, check whether it's the target value is between nums mid and nums high, whether it sort of comes over there. If it comes over there, then awesome. Then you know for a fact that you need to make that you're going to do a recursive call from your search util from your mid plus one to your high. Basically, you know for a fact that's going to be in this range. So you just bifurcating it out like you do in binary search, and just dividing it and getting into that particular area. And if it does not come over there, then you know for a fact that you need to return the value which sort of comes from the low to high, low to mid, sorry. And that's basically very easy to understand. If it does not come over here, if it's not in this range, then obviously you need to check out the value, or basically if it's not on the right side from the mid, you need to check out the left hand side, right? So the way to do that is just write low and mid minus one. And that's basically it. I don't think that there's anything more required over here. Just try running this, and hopefully it should run. And awesome, you can see that you're getting the correct output. You've been given an input, which is this particular rotated subarray, and you've been given a target element as 0, and it was able to, find 0 easily. Let's just go ahead and submit it. And awesome, you can see that's faster than 77 of the Python online submissions. And this is a very simple problem, to be very honest with you, because all you're doing is you're already leveraging how you would use binary search, and then you're just breaking out code apart from there and just splitting it out and just writing your rules accordingly. Again, if you do not understand, all you've done is you've written a utility function, which is a binary search utility function. It's taken a low and a high, and all you've done is you've just checked for what's the sorted array. If you can understand what the sorted array is, and if you know for a fact that this is the sorted array, you just check the range, and if the range is within that range, then you just go towards that direction. You sort of update your low and your high accordingly. And that's basically it. That's how you sort of progress with this entire solution. And again, it's very, very simple if you sort of break it apart, or if you sort of have a lot of use cases. So again, I would urge you, whenever you have an interview, write down as many edge cases as you can, because when you write a lot of edge cases, you might see a flaw in your current implementation. And even in an interviewer might give you an example where the pivot element is at the middle, and everything is sorted and everything is working fine, but the pivot element might be a different case. So you have to handle all those cases as well. Cool. So if you have any comments, or if there's something that you do not understand, do let me know in the comment section below. I would love to handle any of your queries. And if you did like this video, do give a like and do subscribe to this channel. We have a discussion over here, and we would love to have you on board with us. And if you've already subscribed, you're awesome. We all know it. And have an awesome day. Thank you.